So now let's review what is the problem that we want to solve. We have this configuration space, we have this scene, and we want to see whether a robot can move from this location to that location without going through the obstacles. We discussed that the main idea that we have is to define this parametric configuration space where you have some points marked as forbidden where the center of the robot cannot be there. And the idea is that we enlarge the obstacle so we get a picture like this. And then we want to see if there is a path that goes through this free region and reaches the target destination. Yeah, something like that. So before getting to the more complicated problems, there is actually one easy special case of this that we can solve already. And that is when the robot is just 1 point. Okay. So now when the robot is just 1 point, the problem reduces to the following. We have this configuration of space with a bunch of polygons. It's a k polygons where the total complexity is n, which means that the total number of vertices on the edges of these polygons is n. And we're given 2 points inside this free region, S and T, and we want to know if there's a path from S to T. So this is exactly the same situation that we have if the robot is a point, and also it will be the same situation that we'll have once we enlarge the obstacle. So it actually solves both problems in one go. How do we do this? If you recall the point location data structures or the point location lecture, we had this concept of trapezoid decomposition. So again, from every vertex of this obstacle, you shoot a ray up and down until you hit another obstacle. So this decomposes this region, this white region, into a bunch of trapezoids. Some of the trapezoids are triangles, but most of them are just general trapezoids. And then we just want to know if we can go from this location to that location. So on top of this trapezoidal decomposition, we can also implement a point location data structure. So this means that in log n time, we can find which trapezoid we're starting from, and also in log n time we can find which trapezoid we're going to. And now we can observe something very, very interesting, and that is once we have found which trapezoid we're going to or from and which trapezoid we're going to, then the rest of the problem doesn't depend on where the input point is. In other words, because from this point you can reach any of the vertices of the trapezoid. Let's say you can reach this vertex of the trapezoid. And then it doesn't really matter from where you came inside this trapezoid, right? You could just solve the problem for these vertices. So this means that you could kind of compute how is it that these trapezoids are connected. To do that, we do the following idea. Again, you could do in many different ways. So this is just, let's say, one way of solving this problem. For every trapezoid, put a point in the middle of it, and also for every edge of the trapezoid, put a point in the middle of the edge. Then connect these edges, the edges that come from the same trapezoid. So let's say this vertex is going to be connected to that vertex, and also connect the adjacent trapezoid. So you get something like this, a graph like this. Okay, so this vertex is connected to this trapezoid and that trapezoid, and etc. And now we can see that this is basically, we are now reduced to a connectivity problem. Is this vertex of this graph connected to that vertex? Before solving this, we just need to make one simple observation. And the observation that we can make here is that this graph is a planar graph. And to see why this is a planar graph is relatively obvious because all the edges are inside the trapezoid. So the edge that connects this point to that point is inside this trapezoid and so on. So obviously they cannot be intersections because when you connect the center of a trapezoid to its edges, they don't intersect. So this is a planar graph, it has linear size, and therefore we could just store it in such a way that we could solve this connectivity problem. It can be done in essentially linear time. Yeah. So for example, we could run a BFS to see if this one and that one is connected. So therefore, we can compute a path from S to T if the robot is a point robot in n log n time. And where does the n log n time come from? Well, it just comes from the fact that we need to build a trapezoid decomposition. That's where it takes most of the time.